Welcome to this lecture on mathematical physics. Today, we are going to explore a fundamental concept that bridges pure mathematics and the physical world: exact and inexact differential equations. Whether you are studying classical mechanics, electromagnetism, or thermodynamics, understanding this mathematical tool will completely change how you view energy, forces, and motion. Let us dive in and build our understanding from the ground up. To understand exactness, imagine you are hiking on a large, uneven mountain. Your altitude depends on your longitude, x, and your latitude, y. If you take a tiny step east, dx, and a tiny step north, dy, your total change in altitude is a combination of the slopes in those two specific directions. In physics and mathematics, we are often given these directional slopes through differential equations, and our ultimate goal is to reconstruct the actual overall shape of the mountain. This helps us understand the entire system at a glance. Now that we have our mountain, what makes it exact? An exact equation is like a perfectly mapped mountain where all local slopes align into a single, smooth landscape. If you walk in a closed loop and return to your exact starting spot, your net change in altitude is guaranteed to be exactly zero. However, if the slopes we are given do not match up to form a real, physically possible mountain, the equation is inexact. This means it describes a journey that depends entirely on the path you take, rather than a fixed landscape. Why do we care so much if an equation is exact? In physics, exact equations are the mathematical foundation of conservative forces, like gravity or the electrostatic force. When a force field is exact, you can define a potential energy function for it. This simplifies calculations immensely because the work done by moving an object in such a field depends only on where you start and where you end, completely ignoring the winding path taken between them. This is why gravity does not care how many loops a roller coaster makes. The energy depends only on the height. This concept is just as crucial in thermodynamics. Here, exact differentials represent state variables, such as temperature or internal energy, which depend only on the current state of the system. On the other hand, inexact differentials represent path-dependent quantities, like heat and work. Without the mathematical concept of exactness, we simply could not distinguish between the energy stored inherently in a system and the energy transferred as heat. Understanding exactness allows physicists and engineers to predict how a system will behave, ensuring that engines and refrigerators operate exactly as the laws of thermodynamics dictate. Let us look at the mathematical representation. A first-order differential equation is often written as m dx plus n dy equals 0. Here, m and n are given functions. The symbol dx represents a tiny change in the x direction, and dy is a tiny change in the y direction. This equation is exact if the left side is the exact total differential of some hidden scalar function, f of x and y. If it is exact, solving it simply means finding that hidden function and setting it equal to a constant. This constant represents a specific state of the system, much like a specific altitude line on our mountain. When one variable increases, the other must adjust to keep the total change at 0. But how do we know if that hidden function exists? We use Euler's criterion. We take the function m, which is attached to dx, and take its partial derivative with respect to y. Then we take the function n, attached to dy, and differentiate it with respect to x. If these two cross derivatives are perfectly equal, the equation is exact, and a potential function definitely exists. If they are not equal, the equation is inexact, and we cannot directly find a single potential function. Physically, if these derivatives match, it means the forces are perfectly balanced and conservative. If they do not match, energy is being lost or added along the path, perhaps due to friction or an external heat source. Let us solve a classic equation. 2x plus y dx plus x minus 2y dy equals 0. First, we identify m and n and check the cross derivatives. Both equal 1, so it is exact. We start building our hidden function by integrating m with respect to x, treating y as a constant. This gives x squared plus xy plus an unknown function of y called g of y. To find g of y, we differentiate our new function with respect to y and set it equal to n. The x terms cancel, leaving g prime of y equals negative 2y. Integrating this gives negative y squared. Our final solution represents a family of contour lines where the altitude is constant. Now that we have successfully solved an exact equation, what happens when an equation fails our test? These inexact equations often appear in physics problems involving rotation or angular momentum, but we do not have to give up. We can introduce a magic multiplier called an integrating factor. By multiplying the entire equation by this carefully chosen factor, we can mathematically mold it, forcing the equation to become exact so we can solve it using our standard method. Let us look at a specific inexact equation. Y dx minus x dy equals 0. Here, our m function is simply y, and our n function is negative x. As we will see, the slopes do not form a valid potential function as they currently are. To rescue this equation, we will use an integrating factor of 1 over y squared. Let us see how this transforms our impossible mountain into a perfectly mapped landscape. When y increases, the x component grows, but when x increases, the y component becomes more negative. This twisting nature is exactly what makes it path-dependent and inexact initially. First, we must prove that the equation is indeed inexact. We identify m as y and n as negative x. We take the partial derivative of m with respect to y, which gives positive 1. Then we take the partial derivative of n with respect to x, which gives negative 1. Since 1 does not equal negative 1, the cross derivatives do not match. The equation is inexact, meaning we cannot integrate it directly. This sets the stage for our integrating factor. Physically, this means if we tried to calculate work done in this field, the answer would change depending on the exact route we took, which is not what we want for a conservative system. Now, let us apply our integrating factor to fix this. We multiply the entire original equation by 1 over y squared. Distributing this term gives us a brand new equation. Our new m function becomes 1 over y, and our new n function becomes negative x over y squared. We have fundamentally changed the mathematical representation of the slopes. The next step is to verify if this new equation behaves better than the old one. By doing this, we are essentially stretching and scaling our coordinate system so that the previously mismatched slopes now align perfectly into a valid potential surface. Let us test our new equation. The partial derivative of our new m with respect to y is negative 1 over y squared. The partial derivative of our new n with respect to x is also negative 1 over y squared. They match perfectly. The integrating factor has successfully transformed the inexact equation into an exact one. We can now recognize the entire left side as the exact quotient rule derivative of x over y. Integrating both sides immediately gives our final solution. X over y equals a constant c, representing a family of straight lines. Let us visualize what we have been calculating. Here you see a three-dimensional surface representing our hidden potential function, the mountain. Below it, projected onto the xy plane, are the contour lines. These loops represent our solutions, where the function equals a constant c. The red arrows show the m and n components, the local slopes we started with. Because the equation is exact, these local slope vectors perfectly trace out the continuous contour lines of the mountain above, proving that our path is perfectly balanced. To summarize, exact differential equations describe systems where changes are perfectly balanced and path-independent, like conservative forces in physics. We test for this exactness by checking if the cross-partial derivatives are equal. When they are, we can integrate to reveal the single underlying potential function. And when they are not, we can often use an integrating factor to mathematically mold the equation into an exact form. You now have the tools to solve these complex physical systems. Great job!